Okay, this is the last installment of the little lectures on chemical equilibrium. I just want to point out in this lecture that things can get much more complicated than a single reaction occurring in a reactor. In fact, usually the situation is that many reactions are occurring at the same time. And thermodynamics provides a perfectly good framework for dealing with those problems as well. The basic idea from a math perspective is that each reaction has an associated equilibrium constant, and that equilibrium constant serves as a constraint on the final equilibrium in the reactor. Each species involved in those reactions are a degree of freedom. And so you have, as long as there are, as long as you're writing things down correctly, there will always be more species than reactions, or at least as many species as reactions. And so the equilibrium position of equilibrium concentration of all those species is well defined. We basically have to minimize the Gibbs free energy over all of those degrees of freedom, subject to the constraints, which are the equilibrium constants for each of those reactions. So let's see how we do this in practice. We're going to start with a reaction that involves NO and CO gases, and these are among a mix of common pollutants from car exhaust. This is a problem straight out of Davis and Davis's chemical reaction engineering book. Both of them are made in reactions that involve leftover oxygen. And so when we have nitrogen gas combining with oxygen to make two molecules of NO, we also have a reaction that takes carbon monoxide, unspent, basically incomplete combustion product, combines with oxygen to make CO2. The equilibrium constants for these two reactions in terms of the mole fractions of the gases are 8.26 times 10 to the minus 3. So this one's going to only proceed a little bit to the right and mostly be over here on the left. This one for CO oxidation is going to go farther to the right because, of course, CO2 is an extremely stable compound. So Xi here in these expressions is the mole fraction of each of the species. And what we're tasked with doing is to calculate the equilibrium composition of a mixture of N2 and CO and oxygen, starting with a stoichiometric amount of air for those compounds at 1 atmosphere. Okay, so that basically tells us, you know, if I want to burn some amount of CO, I need some amount of oxygen, and that oxygen is going to come in with an amount of nitrogen, and we're going to use all of that to model what really happens is that instead of making all CO2 and nitrogen coming out of the reactor, we're going to end up with CO2 and some NO as well coming out of the reactor, because this reaction also proceeds just a little bit, at least, to the right. So we're going to start just the way we've done before, except that now we have two different independent reactions that can occur. So we start with CO in the reactor at an amount 1 molar. We have to have a half mole of oxygen to convert all of that CO. This is the stoichiometric amount of oxygen that would convert all of this into CO2. But along with that oxygen, along with a half mole of oxygen, if we're going to get that from the air, we're going to also introduce 1.88 moles of nitrogen, because air is 78% nitrogen. Okay, so we have 0 carbon dioxide and 0 NO coming at the inlet. And after this reaction proceeds to equilibrium, the second reaction will have gone an extent Xi2, so that will convert 1 mole of CO into 1 minus Xi2 moles of CO remaining. The first reaction will take nitrogen from 1.88 moles at the inlet. The extent of reaction 1 decrements that by an amount Xi1 because it appears once in the stoichiometric reaction. Each of these two reactions consumes some of the oxygen, and so this is how the two reactions are coupled. They're coupled through their common consumption of the oxidant here. So we have 0.5 moles minus 1/2 mole for each time 1/2 mole of oxygen gets consumed each time a mole of the second reaction occurs. and a single mole of oxygen gets consumed each time a single mole of the first reaction, the one that makes NO gas, occurs. Okay, so how much of the products do we have? We have extent of reaction Xi2 moles of CO2 produced, and 2 times the extent of reaction 1 amount of NO produced. Okay, so the total amount of material that we've made is 3.38 minus 1/2 of the extent of the second reaction. So this now allows us to write everything again in terms of mole fractions. So we had the amount of NO squared divided by the amount of nitrogen at the exit and the amount of oxygen at the exit. These are mole fractions. Notice that I don't have a factor of 3.38 minus 1/2 Xi2 because there are 2 moles in the numerator and 2 moles in the 2 gases in the numerator and 2 gas molecules in the denominator. These factors just canceled. In the other reaction, the one that describes the equilibrium conversion of carbon monoxide, we do have one of these factors of 3.38 minus 1/2 appearing. That's coming from the CO2 divided by CO and divided by the oxygen to the 1/2. We have an extra factor in here of this total amount of gas to the 1/2 because we have 1 mole on the right and 1.5 moles on the left. And so that gives us this factor of 3.38 minus 1/2 Xi2 in the numerator. You can go back if there's any confusion about these and look at the stoichiometric equations for these and the definitions of the equilibrium constants. All we're doing is using our table to fill in these numbers and then equating them to these numerical constants. Okay, so what does that look like to do this solution then? Once you have these 2 equations you have to solve in terms of the 2 unknown extents of reaction, what we have then is that we have a first reaction that could possibly go all the way until it consumes all of the nitrogen. We have a second reaction that could possibly go until it consumes all of the CO, and so that sort of puts lower and upper bounds on those values of extent of reactions 1 and 2. We can solve each of them independently, and what they would give is an extent of reaction 2 in terms of extent of reaction 1. So each of these represents then a curve in that 2-dimensional space, and we want both of these 2 equations to be true, and so we look for the place where those 2 curves cross, and that gives us the equilibrium conversion in terms of 2 extents of reaction, right? So at equilibrium, the first reaction goes 0.037 moles to the right, and the second reaction goes 0.19 moles to the right. Much larger amount of CO being converted than nitrogen being converted, but nonetheless there is some conversion of nitrogen to NO. So if we now plug these 2 equilibrium conversions into our original table, we see that at equilibrium the mole fractions of nitrogen are 0.561, oxygen is 0.112, CO is 0.247, and CO2 0.058. The one that's a surprise here that probably you wouldn't have guessed might have occurred is that you actually do make some of this NO gas. That's 0.022. So things can go on and get even more complicated. In this case, if we look at coal gasification, we start out with solid carbon. We add to it water and oxygen. At high temperature, these will convert into hydrogen gas, carbon monoxide, and carbon dioxide. We now have 3 elementary reactions. I'm sorry, these are not elementary reactions, but they are 3 independent stoichiometric reactions for this process. Hydrogen gas can combine with oxygen to make water. Solid carbon can combine with oxygen to make CO, and solid carbon can go farther and combine with oxygen to make CO2. Okay, so we could have easily, instead of the third reaction, another independent reaction would have been to take the one that we just considered in the previous example, CO combining with 1/2 of an oxygen to make CO2. The important thing is that these reactions, none of them can be written in terms of the remaining 2. And so they're all 3 independent reactions. And if I added that last reaction, CO combining with oxygen to make CO2, I would be able to write that new reaction in terms of reactions 2 and 3. Okay, so we have a complete set for describing these products, and that will allow us to determine the equilibrium conversion if all of those reactions can happen and proceed to completion. So if we were to start from initial conditions where we have 1 mole of water, of steam, basically, when we have 2.38 moles of air, which is well, I'm not sure where that number came from. Maybe I will see in a moment. So then we're going to compute the equilibrium outlet concentration, where we have the pressure is 20 bars and 1500 Kelvin. So we want to compute the equilibrium composition at these conditions. We're going to treat all of these gas species as ideal species, and the first thing that we want to do is to make a table of the Gibbs free energies of formation for each of these species involved in the reaction at each temperature that we're interested in. Okay, so we're only going to do the case 1500 Kelvin. The Gibbs free energy of formation of water is minus 164. Gibbs free energy of formation of carbon monoxide is minus 243. And the Gibbs free energy of formation of CO2 is minus 396. Okay, so notice that I haven't written Gibbs free energies of formation for solid elemental coal or elemental carbon. I haven't written the Gibbs free energy of formation for elemental H2 gas. That's its standard state, is the diatomic, and also for oxygen, right? So these guys have Gibbs free energies of formation of 0 by definition. So now what we're going to do is we're going to use the free energies of formation to get free energies for each of these reactions. So the first reaction has a Gibbs free energy of minus 164. The second reaction has a Gibbs free energy of minus 243. And the third reaction has a Gibbs free energy of minus 396. Okay, so this is remarkably easy in this case because on the left-hand side you'll notice that you always had the standard elemental states of each of these elements, hydrogen, oxygen, and carbon. Okay, so it was a bit of an unusual example, but you can go through and do that algebra. It's all stuff that you learned in thermal. So we make our table again. We have all of these species now: H2O, oxygen, nitrogen, hydrogen, carbon monoxide, and carbon dioxide. These are the numbers of moles of gases in the inlet. And this is the amount of material that you have of each species that you have remaining after each of those reactions has proceeded to a completion. What you notice in the table this time is that there are now 3 extent of reaction variables, one for each independent reaction involved in this process. Okay, so this is something you can ponder here and look at how I did this, but this is all just coming from the reaction stoichiometry. We had reaction 1, making new water. We had reactions 1, 2, and 3, all consuming oxygen. We had nothing happening with our nitrogen in this example, although in reality probably there would be a little bit of NO being formed in here as well. We have reaction 1 consuming hydrogen gas, and we have reaction 2 making CO. We have reaction 3 is making CO2. Notice this one, we start out with no hydrogen, and we end up with minus Xi1, right? So we cannot possibly have a negative amount of hydrogen, and this is going to tell us immediately that reaction 1 is actually going to proceed to the left, okay? So that might be driven by some other reactions, but that is a necessary consequence here. We can't have negative of any species. So the extent of reaction variables that I'm using here, by the way, can have signs that are positive or negative in general, and that's one thing that makes them a little bit more of a mindless approach than dealing with fractional conversions. So with fractional conversion, you often have to identify your limiting reagent and work with that one, the fractional conversion of that limiting reagent, instead of really being able to just allow the math and the optimization to find the appropriate values and signs for each of the variables. So from this point on, It's really a matter of going through and plugging everything in. So we're going to assume that we have ideal gases, so we can write these mole fractions as the mole fraction multiplied by the total pressure as just giving us the partial pressure of each of those species. We're going to do that for hydrogen, water, CO, CO2, and oxygen. N2 is really just along for the ride here. Nothing's going to happen to it along the course of the reaction. And of course, the carbon, the solid carbon, isn't going to have a partial pressure. So if we write down, using the ideal gas approximation, the equilibrium constants, then we have equilibrium expressions that look like this. For the first reaction, we have water as a product. We have reactants, O2, half molar O2, and a single mole of hydrogen. So this is our equilibrium constant there. We have, for the second reaction, we have CO as a product, half molar oxygen again, and solid carbon. The activity for the solid carbon is just 1. It's completely independent of pressure, and it's the reference state, so at all temperatures it also has an activity of 1. The equilibrium constant for reaction 3, we're making CO2 from a single mole of oxygen, and again starting from solid carbon, so this is just giving you an activity of 1. We can go back now and plug in these things in terms of mole fractions. So now we're going to make use of our table and write mole fractions for each of these things, relate them to the total pressure and the partial pressure in that way. So here are the mole fractions plugged in. So this would be the one for water, and then we have a factor of we have some residual factors of the total amount of material made and the total pressure divided by the reference pressure. This is for the oxygen and the hydrogen gas. This is oxygen actually, and this is the hydrogen gas term. That equilibrium constant then is e to the 13.2. Remember where we got that term, where we got that value. That was coming from the exponential of this divided by RT. Then you take that and you once you find that number, you take that exponential, what is called a Boltzmann factor, e to the minus delta G naught divided by RT. That is your equilibrium constant. We are writing that as e to something, so we have to take the natural log of that, which is this number 13.2. Okay, so then you do that for all of these equilibrium constants. You fill things in from the table, and I will move back to the table now so that you can see this. So these are the numbers in the table, and we plug them into the equilibrium constant using the ideal gas law. So we're using this in each case and getting these expressions for the equilibrium constant. We had the numerical values from the tabulated Gibbs free energies, and then the last step that remains is to solve for the values of the extent of reaction 1, extent of reaction 2, and extent of reaction 3.